In the past 24 hours, people uploaded more than 720,000 hours worth of footage onto YouTube. According to calculations made a few years ago by University of Portsmouth physicist Melvin Vopson, this literal mass of visual imagery, along with 500 million tweets, countless texts, billions of WhatsApp messages, and every other bit and byte of information we've created, could be making our planet a touch heavier. It's a wild concept unlikely to be accepted without a ton of evidence. An experiment recently proposed by Vopson based on antimatter explosions might go some way in convincing the scientific community that information might not only have mass, but that it could also be a strange new state of matter. Information theory isn't an easy concept to digest. We can easily imagine the downloading of a code of ones and zeros that tells our computer what sounds and images to display, but information might also be applied to non-digital things, such as characteristics that tell particles how to behave. This makes it an important factor in describing things like the amount of order and changes in energy making up a system. In the early 1960s, the German-American physicist Rolf Landauer predicted a minimum change in energy for erasing information from any kind of system. While it might seem like a small realization, the implications are profound, linking the loss of information with the emission of heat radiation on a fundamental level. Experiments over the years backed up Landauer's reasoning, right down to a quantum level, suggesting there's at least something to the fundamental amount of energy associated with information change. If we also take Einstein's reckoning into mind, as Vopson does, that fundamental change in energy should equate to a change in mass, meaning all of the information we create each and every day contributes a tiny but non-zero amount of mass to the planet. Taken to the extreme, the exponential accumulation of cat videos, Wikipedia entries, Twitter beefs, and TikTok car sing-alongs would lead to some shocking consequences in the far future. Not only could we run out of material to hold onto all that data, but unrestricted digital growth would also mean a significant fraction of Earth's mass will eventually be in the form of digital information. In fact, in 350 years, some experts predict the weight of our digital bits could outweigh all the atoms on Earth. Doomsday scenarios of an information crisis aside, such a theory could change how we calculate mass under certain circumstances, leading to new theories that might give us a better idea of the nature of dark matter. Detecting the incredibly minute shifts in mass anticipated for today's information-dense storage systems is still well beyond our abilities, for now leaving the hypothesis in the fun to think about basket. But a new experiment proposed by Vopson might change all that, applying Landauer's prediction to elementary particles. If we presume an electron's total mass is made up of its intrinsic resting energy and a tiny bit of information about itself, it would theoretically emit a predictable spectrum of energy in the spray of photons released on meeting its antimatter counterpart, the positron. The information in an electron is 22 million times smaller than the mass of it, but we can measure the information content by erasing it, says Vopson. We know that when you collide a particle of matter with a particle of antimatter, they annihilate each other. And the information from the particle has to go somewhere when it's annihilated. Looking for the very specific wavelengths of radiation in the annihilation of an information-laden electron would tighten connections between information as a form of energy within particles, rather than as some other feature of thermodynamics within a broader system. Finding some kind of intrinsic, information-based energy component as a fundamental feature of matter might also qualify as a new kind of physical state. Not only can atoms unite as solids, flow as liquids and gases, disperse as plasmas, and harmonize as Bose-Einstein condensates, they can reduce disorder as information carriers. Until the experiment is conducted, the hypothesis will remain a contentious, if intriguing, idea. But if it turns out to be true, the consequences could be truly massive. This research was AIP Advances.